and I'll hand over.
Hi everyone. So you've already heard from Ulrich, but he hasn't been properly introduced. So our next speaker is Ulrich Paquet. Just something about him. He's originally from South Africa. He studied at University of Pretoria and then did his PhD at Cambridge University. After that, he worked for a few startups as well as Microsoft Research, and is currently at DeepMind. Apart from that, he is also one of the driving forces in promoting machine learning research in Africa and South Africa. He is one of the organizers of the Deep Learning Indaba, and he is also he's recently been appointed an extraordinary professor at Stellenbosch University, where he is busy putting together a master's degree in machine learning. So over to Ulrich.
Everyone, it's really wonderful to be here in Stellenbosch. You're all doing well still? Okay, so this. Okay. I've given this explanation of deep generative models, so variational autoencoders, twice before. So I stand the risk of becoming a bit of a one-trick pony when it comes to giving a talk. But the motivation for this session is to give you very, very basic intuition and building blocks for doing probabilistic inference in deep models, deep neural networks. And I hope that you only walk away with 2 or 3 tricks or key concepts, and if you grasp those, this session would be a success. So I worked in variational inference in the early 2000s, long before the deep learning revolution, and the class of models that we could do inference in was fairly limited. And then roughly half a decade ago now, 5 years ago, this idea of doing amortized inference with deep networks came about by Dirk Kingma, Max Welling, and then Daniela and Shakir, who work with me, Shakir, who was here. And that has really revolutionized and opened up many possibilities in combining probabilistic inference on one hand and statistics with the whole world of differentiable functions and deep neural networks. So there is a recording on YouTube of a previous version of this talk. So I'm going to start with a 2-minute exercise. And you need to pretend that you're a data scientist in a company, and I present you with this data set. I'm not going to tell you anything about it, but just spend a minute or two and talk to your neighbor about everything you can infer about this data set. Just take a minute or two and chat with your buddy. It's okay, you can talk to each other. Okay, data scientists or engineers. Okay, everyone, can you give me a few properties of this data set? Just raise your hand and give me something that you noted. Yes. Anyone? Yes. There's always a white bar. There's always a white bar. Okay. Anything else? Okay. If it's projected as a vector, the bar disappears. if you take the image and you stack it as a vector. So you need to rotate it as a square to see the bar. Anything else? It seems kind of noisy, so it's white-black, but with a bit of speckle noise. Dimensionality? 16 dimensions. Okay, a few other things. What about this index? Who thought about a time series? Oh wow, only like 3 or 4 people. What does 1 to 3, 4 to 10 index? So for the purpose of this talk, it's not temporal. I'm going to assume that all of these 10 images are independently generated. So I'm not indexing as a time series. The main thing I wanted you to see is that I can tell you most about the data set by just telling you the number of the column that gives me of the white column. So if I communicate to you a number 1, 2, 3, 4, or 5, you would be able to mentally completely regenerate the picture. Okay? You can tell your buddy, oh, number 4, and you can imagine an image with a column in number 4. Okay, so if you can do that, then you've arrived at a very important conclusion. You concluded that the data set that I gave you live on a one-dimensional manifold. You need one number to describe the data set, modulo a tiny bit of noise. Furthermore, all you need is one number which, for the purpose of this talk and for the purpose of most VAE autoencoding probabilistic literature, we'll call Z. So Z is 1, 2, 3, and 4, and if I tell you Z, you can generate a 16-dimensional, much higher dimensional image. So this immediately touches on the idea of reliable communication over a noisy channel. This touches on compression or data set compression with deep neural networks. And my next question to you is, if I give you a number Z, how will you render or generate an image as a forward process? So it's actually really easy. I give you a number Z over here at the top, and then in your favorite programming language, you write a function that will generate a 4x4 grid. It will find column number 2, and it will draw the white bar in column number 2. And then at the end, the output of your program is this image. Just voila, it's really incredibly easy. What we're going to do in deep networks is we're going to take exactly this programmatic approach where you've taken your latent variable and you've expanded it to describe your world, and we're going to take that and we're simply going to replace this bar drawing function of yours with a neural network. Instead of a program, it's simply a function. And it's going to take a one-dimensional input Z, and it's going to output a 60-dimensional either matrix or vector, which will be X. So I have a next challenge for you, and the challenge for you is to quickly design your very own neural network or function that will take Z as an input and render X. Okay, just spend a tiny bit of time. It may seem like a very stupid exercise, but a lot of notation is going to follow, and I want you just to tie my notation of parameters to your model that you're going to use in the next hour or so. So just take a minute or two and write down any function or draw any function that will take Z, which I'll now make real valued, and will produce some sort of X. Okay. Okay, so as a quick sample, who had a linear model to produce X? Who tried a linear model? Who did something like a multi-layer perceptron, a function with 2 or more layers, densely connected to produce X? Who tried to draw some convolutional architecture because you're working with an image? Did someone try a convolutional network or deconvolutional process? Anything else that we missed? Who wrote a probabilistic program? Good. Anything else? Okay, so you might have done something like this. You would have said, yeah, the Z is an input. You might have had a set of weights and biases for one layer that would have produced a set of hidden units. You might have had another set of weights and biases for layer 1 and layer 2. And finally, you would have combined this to produce either a 16-dimensional vector or maybe a 4x4 matrix-style output. Okay, so theta in my talk would be all the parameters that take Z and generate X in your network or in your example. Okay, so now we get to the idea of a data manifold. So your example or your function could have taken Z's in on a scale of 0.1, 0, 0.2, or 0.3, and that would have been a valid code to generate the images that you see. You could have also gone for 1, 2, 3, or 4, and that would have generated the images. So you could have scaled this latent code arbitrarily, and it would have generated your data set for you. So I could have given you any kind of scaling for Z to generate X. Okay. The next thing that you might note is that in your data manifold, if you really manage to capture your data manifold, you would have had possibly 2 instances of Z that are somehow close together in Z space, and if your network generated them, it would have produced 2 copies of X that were very similar. So let's just go back. There's one more bit that you need to know, and that is that there is usually some noise on the images. So in the program that you wrote, you probably wrote a program that generated a deterministic image. So now I'm going to ask you to make further assumptions. And the other assumptions I want you to make is to think a little bit about the noise process on your images. So someone mentioned that there's a tiny bit of noise on the black and white images. So take a second and change your model to, instead of rendering a hard image X, change your model so that it can render samples of X. So it still gives Z as input. You'll have loads of parameters theta. And if I run this forward, you should be able to generate different instances of X that look very similar. Just try that for a second. Okay, so I'm very interested. Who of you assume that X is real valued and is corrupted with Gaussian noise? Who of you assume that X is binary and has some Bernoulli or some other kind of distribution as noise process? Okay, you shouldn't really, because I sort of colored it in different shades of gray. So it looks like it should be a real valued output. For the purpose of this talk, I'm going to pretend that X is binary, just because it makes the explanation easier. So what you could do if it's binary is you would have a final output layer of a network that would be, let's say, 16-dimensional. And you take that, and you'd have a unit for every pixel. So pixel 1 to 16. And you'd pass that through some link function, like a sigmoid function. And for each pixel, you'd get a probability of pixel I being equal to white or black, given the value of the unit in there. And as a likelihood, you'd probably write it down as a probabilistic likelihood. So you'd write it down as the link function of AI, which is that red dot, if xi is 1, so you can remove that bit, multiplied by 1 minus the link function of AI, 1 minus xi. So that would give you the probability of X being a white or black pixel with a Bernoulli likelihood. And your network, of course, would produce this. Okay, so what we have here is, instead of a program, I have a probabilistic model that takes in Z, produces X, and I treat theta as parameters in this case, and not as random variables. Okay, so this brings us to the notion of a decoder. Decoder parlance is simply a function that takes Z and it expands it to X with parameters. Some people call it a generative network. So in code, you often see a generative network that takes in a vector Z and it would return some Bernoulli logits, which are the A's that I just showed you. Okay, so if I can decode from Z to X, then it begs the very interesting question, well, if I give you X, how would you revert the process and encode into a Z? So let's say I want to communicate something over a noisy channel. I know that if I give you Z, you can decode. Me on this side need to take X and encode it again. So the easy process that we've just written down is the process from Z to X. And all I want to do is I want to define that process, going from X all the way back to Z. Or in other words, the probability of Z given X. Remember, the forward process is P theta of X given Z. I now care about the reverse process. And probabilistic inference is all about inferring this reverse process. Okay? So there are two key questions that we care about. That is inference and learning. And it's very useful as someone who does probabilistic model to separate these two. So the question of inference is simply the question of saying, you wrote down your likelihood of seeing your data given this latent code. How could you figure out what the latent code or process is given your data? The question of learning is there a better or best setting of these theta parameters that could generate your data? So is there a better setting of theta to generate your data? And these two things are very, very tightly tied or coupled. You can't solve the learning process without solving the inference process. Okay, so that's learning and inference. So how can we reverse engineer this process? Well, it's actually an impossible task unless you make some assumptions very explicit. And the assumption in this case that you at least need to make explicit is your scaling. So I did not tell you whether I measure my Zs in units of 1, 2, 3, 4, or 5, or units of tenths, like I encode my Zs as 0.1, 0.2, or if I somehow decided to add 10 or 100,000 to every latent code. So you don't know that. So you need to make some prior assumptions. And the prior assumptions you need to make is you somehow need to put a probability distribution on what you expect these latent codes to be. Should they be scaled in units of thousands? Should they be scaled in units of ones? Should they be shifted by a factor of 10,000? So this is probably for me the core or the critical contribution that Bayesian inference and probabilistic inference brings to the table. And that is that you always need to make your assumptions very, very explicit for an entire model. So to answer these inference questions, there's actually no way we can do it without explicitly stating our prior assumptions. Okay, so my prior assumption for the next 45 minutes at least will be that our z's are drawn from a Gaussian distribution with zero mean and a variance of 1. So that sort of tells me that it's not, z's won't be in the order of 10,000s. It may sound completely obvious, but it's going to be useful for this talk. And that is that if I were to draw a Gaussian distribution as it is, normalized, this area is equal to 1. Okay, you think this is no-brainer? You'll see in a second why it's important. And from samples from these Gaussians, I need to write a function that will take samples and it would generate observed random variables, x. So the two kinds of things in probabilistic modeling, there are observed random variables and then there are hidden random variables. The two terms, in this case, your x would be your observed random variable, and then whatever number lies on this one-dimensional z line, that would be your unobserved, or your hidden, or your latent random variable. So everyone's fine with this terminology. You might have heard it 100 times. I don't know that, so I'm doing some inference about what you do know. Okay, so now we can ask the inference question. If I give you x, what would z be? And there might be, in your Z space, a whole suite of instances of Z that would roughly generate your data. So because we're working with a probabilistic model, there's not just one Z that could have given rise to the data. The kind of picture you might imagine is that I might have taken this Z and it would have encoded or produced the data. I might have coded another Z sample, and with a good theta setting, that might have given risen to the data under my noise assumption. So if I were to take all of these samples, or all of these options, and visually illustrated them, I would get a distribution. So my question for you next is, assuming that the largest value of my likelihood is for pixel is 1, or largest likelihood value for an entire image is 1, can you try and draw the joint density P of x and z on this graph, on this figure? Okay, so try and draw P of x and z as a function of z, because this is my z-axis, given that that was my image x, and these are the kinds of samples that generate the image. Everyone, do you wanna have a go? Okay, so the joint density is the prior P of z, which is this thing in red, which you somehow have to multiply with a likelihood function, which I tell you is upper bounded by 1, because you've got binary pixels. And you just need to write this as a joint, as a distribution, as a function of z. Okay. Okay, who's struggling? Who's struggling with this? Any questions? Okay, everyone, give me a thumbs up if you have an idea of how to do it, and just a thumbs down if you still need a bit more time. Thumbs up. Do you need a bit more time to try? Okay, shall I give you another minute or so? Okay, so here's how I would go about drawing the joint density as a function of z in terms of actual intuition. So so I know the value of this function is between 0 and 1. The probability of a binary pixel, if you hit it correctly, it's like great, it's 1. If you miss it completely, it's 0. Then I know that in this area over here, there are no instances of z that sort of seem to map down to x. And then as I get to this area, there are more z points that are likely to generate and get all my pixels correct. So this function would go higher. Somehow in this area, hopefully it's equal to 1 or close to 1, and then over here it should tail down to 0. So if I, in my head, try and multiply that function with this Gaussian prior, I should get something that looks like this. Well, maybe a bit like that. Okay? So this function that I've drawn is the joint. You also see that because the likelihood is less than 1, this function always sits underneath the prior. Okay? What that means is that the area of that function is always smaller than 1. Okay, so I know the area underneath my prior integrates to 1. So I know that the area underneath this green function that I've just shown you is smaller than 1. So now I care about the likelihood of my data. And the likelihood of seeing this image over here would be the probability of my image given z averaged over all possible z settings as given by my prior. So I can write a likelihood as the probability of x given my parameters is the integral of p theta of x and z dz. Okay, and that integral is essentially the area under this curve that you've just imagined. Okay, well, this should have been a 1-minute exercise. What is the area of this green curve? The area of this curve, I've just said, is just the likelihood times the prior integrated. And whereas I can compute the area under my prior, that is exactly equal to 1. For any of these deep networks, there's no way, except for Monte Carlo methods, that I can tractably compute the area underneath the screen curve. Because I need to sample from the prior, generate, and see how far I am from the data. So this I can compute. That area I can't compute. Okay, so that's one thing to remember. What is the relationship to the posterior distribution of the screen function? The relationship to the posterior is simply taking the screen curve, dividing it by its area, and renormalizing so that the area is 1. So in this case, I have a prior with an area equal to 1, and shifted to posterior with an area equal to 1, and the likelihood, or what some people call the marginal likelihood, because I've averaged over my Z settings of my latent code, that is the normalizing constant and the likelihood that I care about. And that's the number that scales my posterior so that the area under the green curve is equal to 1. So that's the relationship between the two. So that's how I get P of Z given X. If only I could compute that number that tells me how to rescale it. If I can compute that marginal likelihood, I'm fine. I've done inference, and I'm home safely. Okay, so in this case, I think all of you are very familiar about this, of this. So I need to write down the evidence for all my points, not just one data sample. So if I assume that they're independent, conditional on all modeling assumptions that I've made, I would just take the product and assume they're IID data points. That's really easy. But what I want you to note is that if I take the product of lots of marginal likelihoods, I essentially take the product of capital N, because there are 10 points. I take the product of 10 areas. And these are 10 areas that I can't compute. So to get rid of the log, the product, we would often take the log and look at the log marginal likelihood. So I'm now going to put my entire data set on one slide and see what it looks like. So here is the evidence for my entire data set, for some setting of my parameters and decoding it. So the evidence for my data, the full data set, is essentially the product of all these green areas over there. Okay? It's really easy. That gives me p theta of x. That is fine, but it doesn't actually model the data manifold. So what will I do, like very, very intuitively, if I maximize the likelihood for my entire data set? Well, looking at the picture over here, you'd very quickly notice that there are some areas in Z where maybe there aren't settings of your neural network that would generate any images that look like they live on your data manifold. So there's sort of holes in your latent code. The second thing is that maybe you can change your generative model so that these gaps are filled in as well. So if you think about maximizing the likelihood, you can almost think of a method that would try and take all these green areas over here and then inflating them and scaling them so that they maximally fill the area underneath your prior. So the kind of solution we want, if we were to maximize it, is to change our theta so that these guys move around so that I end up with a solution that looks like this. So that's a lot better. So this means that in this area of my prior space, I would still encode prior samples down to my image space. So I've actually captured the data manifold. Okay, so that is maximizing the evidence. I have a comment here, and it's actually interesting that no one picked up on this when I asked you to describe the data set. So if you look at the data set, you have noticed that there are twice as many images with a white bar in the second position than there are with a white bar on the left or on the right. So if I have a really good flexible encoding, I can expect that my prior space of Z, which is real valued, would be partitioned so that 40% of the prior mass would be decoded to images with a bar in the second position, and then 20% for the others. So essentially, you tile your prior so that your data fits proportionally underneath your prior. Okay, now for the tough part. How on earth will we learn this? Well, learning's very easy on paper. So I want to maximize the total area of all these green curves as a function of theta. That's essentially what maximizing the evidence the marginal likelihood does. Or I want to maximize the log of the sum of the total area. Okay. I have here some strategies. One is to do a full stochastic approximation with Monte Carlo methods, etc. Yes? Yes, yes. Yes, exactly. Given your data. That's exactly what you want to do. Yes. Yes. And you want to find, so the question is like, the question is whether we want to have the average posterior look like, the aggregate posterior look like the prior, yes, and we want to find parameter settings that will maximize that matching or that spread. Okay, so I told you, okay, let's just go back. Well, so there are a number of ways in which we can do this, in which we can approximate the areas under these green curves. One is with the Monte Carlo methods. The other one is with deterministic methods. And we're only going to focus on deterministic methods in this session. So the kind of question we want to ask is, we want to compute the integral of the joint under Z, the area underneath these green curves. Because if we can do that, we can maximize that area. The only problem is that we have no way to compute these areas, so we need to approximate it. So this is where approximate inference comes into play. And I'm now going to very slowly explain you one way to do it, and that is a variational bound. And I'll try and do it, and you've seen it a number of times before in sessions in the summer school. I'll try and explain it pictorially, because I'm a very visual person, so that's how I figure out what's going on. So I have a green curve, which is the joint of x and z as a function of z, and I can't compute that area that I actually want to maximize. One strategy would be to find a function that looks a little bit like the green curve that I can compute, and then maximize that function. And that's what we'll do. So here's the approximate posterior that we've defined. So I'm going to define a function that I'll use in the process to maximize this green curve. And that is what we call an inference network. So it's a surrogate for the posterior distribution that we can't compute, that I showed you for the reverse process. So my reverse process is I give you an image and I encode it back into Z. And I'll write this as Q because it's an approximation, and it's going to emit Z. So I actually want Q of whatever parameters phi I have of Zx should, in a wonderful world, be approximately equal to P theta of Z given X. And the one on the right-hand side I can't compute, this one I should actually be able to compute. And this idea of writing an approximate function is called an encoder, or an inference network. So, so typically, an inference network in this world would take the image as input and emit, in this case, a Gaussian distribution over Z. So instead of giving a sample, I would take X, and I'll write a network that would emit the mean of this Gaussian distribution and the variance of this Gaussian distribution as a function of X. So I just want you to think a little bit about that notation by trying to write your own inference network. Okay. So as a 3-minute exercise, try and write a network that takes a 60-dimensional input X as input and produces the parameters of a Gaussian distribution, as in its mean and its variance. And then tell me a little bit about your parameters. Okay, then everyone, you're very free to ask questions in the meantime. Is there anything that does not make sense? Yes. Yes, yes. Yes. Oh, okay. Do you mind if I flip back a few slides just to answer this? Okay, so I cheated a tiny bit as a confession, in that I assumed, let's just go to this area that's actually this critical thing we want to estimate. So I assumed that my data is binary, 0 and 1, and I have a Bernoulli likelihood in this case, for the purpose of this example. So if I have a Bernoulli likelihood, I have P theta of X given Z would be the product, if I assume all my pixels are independent, so those are my pixels, probability of xi given whatever function, deep generative function I got from Z in position I. That's right. And I wrote each of these individual pixel probabilities as a sigmoid of f of Z in the position I to the xi, and then 1 minus the sigmoid of f of Z in the position I to the 1 minus xi. Okay, so this expression at the top was the probability for one pixel given the last activation unit. And the product of these two sigmoid functions are always between 0 and 1. So that's now very convenient to help my explanation, because they're always between 0 and 1, I know that if I get every pixel correct, the product of all 16 pixels would spike at 1. If I get one pixel completely wrong, it's going to drop to 0. If I'm sort of almost there, I'd get a value of like 0.9, 0.8 for my pixels. So if I then multiply that function that's upper bounded at 1, when it sort of nails all 16 pixels correctly with the prior, it still has to fit underneath the prior. So that helps me to think about how this green function should actually maximally inflate to fit underneath the prior. You can try and do this for Gaussian and other distributions, but it's just easier for the sake of explanation to think of these inflating green balloons underneath the red function and changing parameters to make them maximally inflate. and spread over the entire space of Z samples in your prior. Does that make sense? Okay. Any other questions so far? None. Okay. So I mentioned that I can't compute the area underneath the joint. So I'm going to approximate my posterior. And an example of a function would have been a multi-layered perceptron, or a convolutional network, if you work with very high-dimensional images, or a ResNet, or a linear model, or any kind of architecture that you really fancy. But your architecture or your function should emit 2 numbers instead of 1. It should emit a mean and a variance. So even though there's one Z, I need to have an architecture that will take in an X as a 16-dimensional input, and it would have some layers, and eventually, at the end, it's going to emit 2 numbers as output. One would be the mean of a Gaussian, and one would be the variance of a Gaussian. And I'd write the mean as that, and the variance as that, and all these parameters over here would be phi. Okay? So I can differentiate. If I know the mean and the variance, I can differentiate this entire chain back to X. A few interesting things to note, if you were to actually do this in practice, is that your variance should never be 0 or less than 0. So you need to add something special in here to either exponentiate it or ensure that that number does not drop out as a negative number. Okay, so you know what your parameters phi are. So when people speak about encoder-decoder architectures for data, what they mean is something very simple. It means that you have 2 functions or 2 neural networks, one that will take your image as an input, so I've written it as one long row vector, and this function is going to give you a distribution for Z, a mean and a variance. At that point, I would sample Z, so I'd have one instance of Z, and I'd run it through my decoder, and I'd generate random images X. So that is the idea. I want to just interject with a very side thought. Who of you have heard about principal component analysis? Okay, almost everyone. So this is really cool because PCA is a linear model. Here's the relationship. In PCA, you typically take a random sample Z from a Gaussian 0 identity distribution, and then you'd write X as X is equal to some weight matrix times Z. Okay, so the Z should have a little stripe underneath, plus maybe some offset M, plus white Gaussian noise. So essentially, in PCA, P theta of X given Z is a Gaussian distribution, and its mean is W times Z plus M, and you've got diagonal variance. Now, because the whole family is Gaussian, and then there are other families in which you can do this, I can write my inverse Q of phi of Z given X exactly. And in this case, if you do PCA, I can take an image and I can immediately down project it to the latent principal components in a probabilistic way. So in this case, instead of writing Q of Z given X, I can write the posterior in probabilistic PCA. What's more, these thetas are then my weights. My encoder and my decoder share the same parameters because I can do exact inference in this case. So you'd notice that instead of having a phi here, I've got a theta over there. So that's the PCA connection in the linear case. It's only that we work with deep networks, so they're nonlinear, so we need to have other tricks. So there's PCA for you. Okay, so just to recap, I'm going to approximate my posterior. And now I want you to think about the ratio of two distributions. The ratio of two distributions, in this case, would be the ratio of the green distribution and the blue one that approximates your posterior. So this red dotted line that I'm showing you here is the ratio of green divided by blue. So over here I'm dividing by tiny small numbers, so the red line shoots up. Here I'm dividing by a number that's much larger than the green one, so the red line should shoot down. Furthermore, I'm going to add a constant line at, for one data point, the marginal likelihood. So I have a challenge for you. And your challenge is to try and figure out when this red line over here would lie exactly on the gray line visually. Just take 30 seconds. Some of you can do it without thinking. Okay, any answers? Sorry there? Okay, so the red line is going to lie exactly on this gray constant line, which is P of x, if your encoder is scaled as a constant of your prior. Yes, exactly. So, I can write the top equation for my red line as P theta of x given z times my prior z, and I've completely done it the wrong way. I can also write it as P of z given x times P of x. So the previous way I wrote it was the easy way. I know the prior, I know the likelihood. Now I'm writing it in the terribly hard way. Both of these now depend on theta. So that's a different way to write the top function. And I divide it by the bottom function q of z given x. And to have this red line sit on top of the gray line, which is equal to the quantity that I'm interested in, basically, these two functions would have to cancel out, and what remains is my marginal likelihood. So these two functions have to be exactly equal, which means that my approximation, or my encoder network, for every input should look exactly like the posterior. So that's an ideal world, right? That's the ideal world we're going to strive towards, this gold standard. Our massive challenge would be to let these two functions, this ratio, be equal to 1 as far as you possibly can. This is today's explanation. I've tried to explain it in different ways. So how on earth will we get this flat line? How can we make this ratio as close as possible to 1 in the areas of data that we care about? For instance, maybe my true posterior puts no mass over here. So I couldn't care less what this ratio is in this area. But my true posterior, this green function, this thing that encoded z's back to images, really cares about images and encodings in this area. So over here, I might want to have this ratio as close as possible to 1. And with this intuition, there's actually a massive suite of approaches you can take. There's a whole family of divergence measures, F divergences, alpha divergences, different crazy approximations, Pieta Kikuchi from physics. The world's your oyster. We're going to pick one, and that is a variation, a lower bound, if you know alpha divergences, it would be at alpha equals 0 or alpha equal 1, minus 1, depending on how you scale it. And it's a nice divergence because it's going to lower bound the marginal likelihood. So here are the steps I'm going to take to get to a flat red line. The first step I'm going to take is to cheat a bit and take the log of this function. If I didn't take the log, I could have taken another approach, and that approach would have been an importance sampling estimate. I'll just write down the importance sampling estimate for you, and you'll see why the log is useful. So if I were to compute, try and get this this gray line with an importance sampler, so hopefully Ian Murray will teach you a lot about that next week. I would write, now I have almost no space. I would write p of x as the integral of p of xz, and that is equal to the integral of some q of z given x, p of x xz, so the joint green thing divided by q of z given x, and that is equal to the expectation under q of z given x of this ratio over here. Right? You can all see that. So how I could evaluate it, for instance, is to just take loads of samples from my blue distribution, compute the ratio, and then average all these ratios. Only issue is in high dimensions, this thing blows up like you can't imagine it. You can show that it's going to converge to the mean, but often the variance of this estimate is going to be infinitely big, even in the most trivial of cases. So we don't want to do that. So hence, we take the log of these two, and the log is safer. Second step after taking the log is to then take the average. So I'm going to take this log, which is this red function, and I'm going to multiply it with my blue function over here. Now, first of all, you might have noted that before I took the log, this red curve was always above 0. Now suddenly it can dip below 0. So I multiply these two together, and I'll get this purple function over here. Third step is to then compute the area underneath the purple function. So take logs, multiply as a second step. Third step is to compute the area. So the third step is then to take the integral of this over dz, which will be the same as the expected value under my blue function, q of z given x. And now I've got the log ratio in there. And now this purple function has a very, very, very special property, which we'll derive in a little bit. And the special property of the purple function is that if I take the area underneath this purple function that I've just defined, and I exponentiate it, that number is always going to be smaller than the green area. So you can think of a strategy, once you have this set up, that sort of goes like this. I want to, in the original image that I showed you, I want to inflate these green functions to be as big as possible. I can't do that, so I define this purple function that sits underneath the green functions, and now I inflate them to be as big as possible, and then they squeeze the green functions to be as big as possible. So I maximize a bound in this case. Okay, so we'll get to this in a second. And then the last step after integrating is then to move around this blue function. So step 4 would be to move around this approximation and its parameters so that this ratio can get closer to 1. Okay, so you can see that as I move this blue thing, this green area becomes bigger, and this goes down, and that function might go up a bit. Okay, so the strategy for variational inference, and the summary is this. I usually have an unnormalized posterior distribution with an area that I cannot compute, and I want to maximize that volume for all my data points jointly. Then I would pick some family Q that would encode an image, X, into Z, but I can compute the area underneath that curve, at least stochastically. And then that curve is defined or designed so that it has a special property, and the exponentiated area of that curve is smaller than the area of that curve, and we just inflate both. Okay, it's a very tricky concept to get your head around, but I'll just reiterate the strategy and then we'll explain it in detail. So the strategy is that I'm going to make the green curve as big as possible by changing the parameters of my encoder, which are going to effectively increase the area underneath this purple curve. And then, because that's bigger, I'm going to change my generative model to make the green curve even bigger. And then iteratively, or jointly repeat this process. So let's put this intuition into an objective function. Okay, so the objective function would be, and you've seen it many times before, just raise your hands if this is very familiar to you. Because I don't want to insult you by explaining it very slowly if you think it's utterly trivial. Raise your hands if you'd like a fairly detailed explanation again. Okay, cool. I was hoping for that. So the objective function is usually this. It has two parts that you want to maximize. It has a KL divergence that tells you how far your encoder is from your prior, and this thing's always bigger than 0. And then it has another expectation of saying that if I manage to sample Z from my encoder, how well it's going to decode into another image. And I maximize that for all data points. So this is the evidence lower bound derivation. But before we do that, I first want to just make sure that everyone understands Jensen's inequality, because it's mentioned a few times in the summer school. So I'm going to ask you to take 2 or 3 minutes and draw log as a function and convince yourself that this inequality that I've shown on the board is true. Okay, so the inequality is a function of Z. So you'll have an x-axis, a z-axis, named Z, and there's going to be 2 points, Z1 and Z2. And for these 2 points, you'll have to draw log as a function, and then convince you that the function on the left-hand side is bigger than the function on the right-hand side. Okay, who's happy? Who's got it? Who needs a bit more time? Bit more time? Okay, bit more time. Okay, I see that I only have 25 minutes left. Okay, and I actually have quite a lot to cover still, so I apologize for going so slow, but I think it's important to get the main concepts down first. Okay, so here's Jensen's inequality in one image. So the log is a concave function. So this red function at the top is log z, or log of its arguments. 2/3 times Z1 plus 1/3 times Z2 would be this point in the middle, if Z1's over there and Z2's over there. So, log of 2/3 Z1 times 1/3 Z2 is the point on that side, at the very top. And log of Z1 is that point. Log of Z2, because log of Z1 is that point. Log of Z2 is that point over there. And then 2/3 of log of Z1 plus 1/3 of log of Z2 would just be 2/3 down that line. And you can see that the one green dot is smaller or equal to the other green dot. Okay, so that's Jensen's inequality in a nutshell for you. Okay. So to prove the bound, I'll do it in the following way. I'm going to start at the top, and I'll write the integral that I care about. Then I'll do a trick, and the trick is that I'm going to multiply and divide by the same Q function. So this is the ratio you've seen all along, this dotted red line that I've showed you, the ratio of P over Q. So multiply and divide by Q. So that's still equal. And now the continuous version of Jensen's inequality kicks into play. So in the image, we had 2/3 of Z plus 1/3 of Z. That's a probability, the 2/3 and 1/3. It's got two atoms, 2/3 and 1/3. Now, if I make that 2/3 and 1/3 a continuous probability, as in Q, the same lower bounding technique still holds than what you showed for the sum of two atoms. So the sum of two atoms just becomes an integral, and in the same way, we also get a lower bound. So what happened, in fact, I think it's easier if I just show it to you over here. So what happens in Jensen's inequality is that the log, you'll see there's a log, and there's a sum or an integral over some probability distributions. In this case, it's 2/3 thirds. What happened here is that the log moved inside the sum or the integral in a continuous case. So the log that was outside the sum suddenly shifted inside the sum of the 2/3 third. And the same thing happens in the derivation of the elbow, evidence lower bound. This log that was outside the sum, 2/3 third, shifts to sit inside the sum. And instead of having a 2/3 third sum, I just have an integral, and this Q is like my 2/3 third bit. So that's how Jensen's inequality works in here. And then I can rewrite this thing. I can rewrite it just by expanding the log, and I get two terms. A reconstruction term, which is the expected encoding, minus some KL divergence. So this P just shifts over there. And this is the KL divergence, or Kullback-Leibler divergence, between my encoder and my prior. And then I've got my reconstruction over there. Okay, so that's the thing I want to maximize. So I can compute the first term, this expected log likelihood. So now I'm only going to focus on the orange term. I can compute the expected log likelihood with Monte Carlo samples. So I can compute it by taking loads of samples from this thing and then putting it through a log and averaging. So, in other words, I can, because I have my encoder network, I can take an X, encode it into its mean and its variance through my encoder network, and draw capital L samples, or loads of samples, from this Gaussian. It's really easy to draw samples from a Gaussian, and then I've got them, all my Z samples. Really easy, and then I compute the log likelihood. So for each of those samples, I would decode. And my expected log likelihood in this as the Monte Carlo estimate would then be, instead of computing this expectation analytically, I write it as drawing Z from my encoder and drawing loads of Z samples, and then I just plug these samples into my log likelihood and normalize. And that gives me an expectation for the first term. Even I apologize if I go faster than you could keep up, but I do want to just get through a few key concepts before the end. Okay. So here's the key issue, is that I I can compute this expectation, but once I have samples, these Z samples, I can evaluate it, but I can't compute gradients. So the problem is that once I have Z samples over there, so I have Z samples, so I can estimate, but it wreaks havoc for taking the gradient with respect to my encoder parameters phi. Because if you look at this bottom expression over there, my Monte Carlo expression, there is essentially no appearance of my encoder parameters. They don't appear in the estimate. The only parameters that I see are the thetas. And that is a problem. It's a problem because my process would be to take X, sample, forward compute, and then I can take derivatives with respect to theta, my encoder network, my decoder network, and then the dependence on the previous parameters has completely disappeared through this hard Monte Carlo sample. So the next trick I'll explain to you is what's called the reparameterization trick. And all I will do in the next 2 minutes is I'm going to explain you a trick that will make this arrow go all the way to the back. And the idea is this. Just focus for a second. The idea is this. Instead of drawing Gaussian samples from the original distribution after I've given you the mean and the variance, I can also draw Gaussian 0-1 samples and then essentially transform them to look like the samples I care about. So for instance, I could equivalently draw the same samples by taking Gaussian 0-1 samples, so there's 0, variance 1, and I multiply or I squeeze the samples by the standard deviation of my network, and then, so those are my samples, and then I add the prior, and essentially I get these Z samples again. So I'm going to write this process in the next slide. And I'll do it over here, and so now I write the same Monte Carlo estimate by, instead of writing it as a function of samples over Z, I'm going to write it as a function over Gaussian 0-1 samples, as you see over there. And where I plugged in the Z samples as before, I'm going to plug in an expression for Z samples. And the expression is my Gaussian noise multiplied by standard deviation plus the mean. And now if I evaluate this as a stochastic average, the expression looks like this. So I've taken all my samples, multiplied them by the encoder to get Z, and I decode. And in this setup, you'll see something really cool. You'll see, we still have the decoder parameters. But if I look closely at this equation, you'll also see, voila, over there and over there, you see the encoder parameters. And I've not blocked or disappeared them away, or blocked them away. So what I've done with this reparameterization trick is something that's really nice, and that's that if you were to write this whole process as a computation graph that you can differentiate, I've written it in a way that my noise is introduced from outside or external to this computation graph over there. So it means that I can evaluate, but very, very nicely, I can also take derivatives now all the way through because theta and phi appear. Okay, so that's called the reparameterization trick, if you've never heard about it before. So, lastly, my albo for the full data set would just be, that's the albo for one data point, and I would just sum it, albos and evidence lower bound, take mini batch samples, plug it into my favorite stochastic gradient descent optimizer, and run with it. Okay, so in the last 15 minutes, I just want to mention a few interesting things. Okay, so people often think about this as a picture, an encoder network, it's a convolutional network that gives you a mean vector with mean standard deviation. You sample your Z, you decode, and you get your cat again, or whatever favorite thing you want to model. It's another way to view it. Some MNIST examples where you can see the Z space, but now with real digits. There's some very interesting work that uses this. One is to represent scenes from different camera positions into a latent code vector. So if, for instance, if I take 2 pictures of this podium, I can encode those 2 pictures of a scene, and that could be enough to give me a full 3D sweep of what this podium would look like. You could also extend it to, okay, so here's an example of taking some pictures of a scene and rendering it in a map. I want to get to some more technical stuff. You can also not think of Z as a single vector or parameter, but maybe some latent code that lives in a temporal domain. So if you're interested in speech or polyphonic music or etc., or navigation or Kalman filters or any engineering problem, you could make this latent Z code have a temporal structure. And instead of encoding and decoding with a single shot, you can make both your encoder and your decoder a noisy recurrent neural network that tracks the same latent structure. So you can make these models sequential. So I want to end with a few tricks and thoughts because I think they would be quite useful. Another way to think of variational methods is to explicitly lower bound the function you want to integrate. It's not always possible, but this happens in EM algorithms and in older style variational inference. So instead of trying to maximize this purple thing that I constructed for you, you can also explicitly write down a blue function that tucks underneath the green function, and then maximize both of them jointly. I just want to show you how that's done very quickly. So in an EM algorithm, who of you have heard about the expectation maximization algorithm? Okay, so in an EM algorithm, the mechanism is very much the same. In an EM algorithm, you actually, if you look under the hoods, write the blue function underneath the green function. And the E step would then take your blue function and adjust its parameters so that it becomes as big as possible. And then your M step would then take your joint and it would then adjust its parameters so that it becomes bigger. So you often see literature of EM that has these two bars that move up. So that's the idea of having these 2 bars that move up. If you are used to, or if you ever use logistic regression or sigmoid belief networks, there's another kind of bound that uses this, and it's called the Jacola-Jordan bound. I'll explain it to you in 1 minute. It's a tractable bound for if your green function has the following form. Your green function is the product of a Gaussian times a sigmoid. So a sigmoid would look like this, a Gaussian would look like that, and the product of the 2 often have like a funky shape that's like that. And this would be a green function. Sorry, this pen can only write in red. And the Jacola-Jordan bound takes a Gaussian and it writes a Gaussian that exactly tucks underneath this product of the 2 functions, and it touches the function twice. And then in the 1990s variational style literature, you would have optimized the parameters of these local functions. So you'd have as a surrogate bound. Okay. There are also other ways in which you can explicitly lower bound this function that you want to optimize. So if you read Tom Minka's thesis, he's got a really nice section in chapter 2 in there. The idea, for instance, is that this function that lower bounds could also be some variational bound. So in this case, I introduced another random variable y, and then I had an approximation q over random variable y with Jensen's inequality, and I exponentiate this because there's a log over there, and voila, that already gives me another g function which has a form that I can write out that also becomes a blue function that sits underneath this green function. So this is the kind of thing you would mechanism you use to derive an EM algorithm as a iterative lower bound. I want to say a few words on collapsing the prior. Who of you have heard about this idea of collapsing the prior? It happens very frequently in variational inference. It happens when you have, for instance, Z in R and whatever that star is. That's quite a kind of a big number. And then you've got Z1, Z2, and your encoder would always pick a number of distributions and make the encoder exactly equal to the prior for that component. So it means that you would often add more components or dimensions to your latent code, and your model would completely ignore it. So you give it excess capacity, and your model ignores that. And that is kind of problematic from a Bayesian inference point of view, because the Bayesian inference point of view says, well, you know what, I make my models bigger and bigger and bigger, and I just integrate over the parameters, and it uses all parameters. In this case, I make my model bigger, and it chooses to prune, or self-prune. And this has been known since the 90s. If you write hidden Markov, variational methods for hidden Markov models, and you make your hidden state bigger, it self-prunes, it truncates. If you were to do a low-rank factorization of a matrix, let's say in recommender systems, and you make the latent dimension of your low-rank matrix bigger, you do a variational approximation, that also self-prunes at a certain dimension. David Mackay wrote about it in the 90s, and it has very interesting physical interpretations. And collapsing the prior is purely a function of the elbow that we write down. If we write down a different loss function, the prior would not collapse. And of course, people have 1,000,001 tricks and trades to train so that the prior does not collapse. Sometimes you would do annealing, so you would first train an encoder-decoder with no KL penalty. So you would never ever encourage your Z to be close to the prior. And once that's fixed, you would sort of slowly, so you first overfit and then go, and then introduce your regularizer. Lastly, there's this idea of making the bound tighter, as in importance-weighted autoencoders. So I'll explain this, if you're interested, as the last trick that maybe you can take home. So the idea of an importance-weighted bound is to take the bound that I've just shown you, and now I'm going to just subscript my samples with 1, because I've taken one Z sample for every evaluation that I do. So I just subscripted it with 1. And after that, I'll write down a next function. So this one is subscripted with 2. And instead of drawing one Z sample, I draw 2 Z samples. And I change the inner mechanism of my function that I averaged a little bit. So instead of having one sample, I have 2 samples over there and over there. And I take the average between them and then the log. And then that becomes my new L. Okay, so instead of one sample, I do 2 or 3 or 4 or 5. Now, what can you say about this 2 sample L? We only have a few minutes. I'm not going to let you work it out yourself. But you did the picture on Jensen's inequality earlier. So Jensen's inequality just says, well, I've got a log of half times half of 2 quantities. So I can pull the log inside the sum. So that would be the bigger than the expected value. And now I have half. I pull the log inside the sum, so it becomes log the first ratio plus half log the second ratio. That's Jensen's inequality for you that you drew on your pieces of paper. And that is then equal to half, because this is just a constant, and there's a sum in the middle. Half the expected value of the first log plus half the expected value of the second log. And then if you look very carefully, this first log bit depends only on Z1, my first sample. The second log depends only on Z2. So each of these is an average over one random variable that are drawn from the same distribution, which means that I've got half and half times that thing, which is just the expected value of Q blah of log of the same ratio, which is equal to L1, division with one example. So now I've shown you in a very easy way that you can construct an estimate that uses 2 samples that's a better bound than the elbow that I've just given you. Okay, so I've just shown you this derivation. So then my guess, my question to you would be, can you guess what the many sample estimate would be? Of course, that's really trivial. So now in this case, I can write an elbow with k samples, and that elbow would be the expected value of z sample 1 to z sample k. And what would happen here is I take a log, and voila, you've all guessed it. I've got 1 over k samples, some little k is 1 to big K, b theta of blah divided by q theta of blah for sample k. And that's it. So that's an even tighter bound. And you can show that these bounds stack up. So L2 we've shown is bigger than L1, is bigger than, and in certain conditions this becomes exact. Okay, so that's importance-weighted autoencoders in a very easy nutshell for you. Last one is auxiliary variable methods. I can introduce. Okay, so it's very presumptuous to assume that everything you see in the world can be collapsed to a Gaussian manifold. And so a lot of work is done to get rid of that crazy, unrealistic assumption, because we know the world is not Gaussian and smooth. It's super heavy-tailed and noisy. So the idea of auxiliary variables is to introduce extra fake random variables that have no bearing on reality at all. So the idea is that you have a generative model where you generate z from x, and then you write any crazy function where you sample some any function that produces noise a. Doesn't matter what that a is. And then I write an inference network. So the beauty here is that I can integrate out a like that, and the model does not change. The beauty here is that I can now write a bound over a and z, which is essentially a bound on the original function, because a is noise. We don't care about a. But we can write an encoder that has this form. We can write the encoder as z, depending on a and x, it's noise, and then an encoder for a from x. So what that then does is it creates an encoder, which is q of, q of, so you want q of z given x, and that is the integral of q of z given x and a, q of a given x, dx. And then if you average over this noise that you introduce, this thing becomes non-Gaussian. So that's one trick you can try and apply, as in auxiliary variable models. So a last thought before we conclude is David Bly spoke to you about stochastic variational inference. If you recall his lectures, he says stochastic variational inference work very well on these things called conjugate exponential families, of which the Gaussian distribution is 1. So a thought, a very promising research direction, is to not assume that this prior is Gaussian, but that it comes from some very structured conjugate exponential family distribution. So imagine a hidden Markov model, a linear dynamical system, a mixture model that has different modes for the Gaussian, and then you would set up your methods so that you have a part at the bottom that does the traditional tricks with your elbow, with your reparameterization trick. So let's say it's a reparameterization trick over there. And then you have something at the top which was Gaussian 0, 1, but maybe now you want to make that prior something like a mixture of Gaussians. so that it's flexible to distribute its mass. This thing at the top will live in a conjugate exponential distribution. So you can read some of David Duvenot's work to get an idea of how this is done. And you then have two styles of gradient descent to make this thing work. So here, at the bottom, you could plug in your favorite optimizer like Adam or normal gradient descent because these are parameters theta. And at the top, you can pull in all your notes from David's course or lecture and do stochastic variational inference in this mixture model or this conjugate exponential model. And then learn these two structures jointly. So then essentially you can learn a really flexible prior by using all the techniques from the 90s and early 2000s, and then have any crazy confnet here at the bottom, and use more recent techniques. There is so much more to say on this. Do you have any time for questions? Otherwise, we can just have a discussion over lunch.